Okay, let me know. I'll any send emails. Okay, so the book which we are going to follow in the course largely is Crystal Graph Theory book, and this course, I don't know when last I taught in boards. Okay, and this course will be taken by me. Let's see, I'm not around. Okay, so how many have seen graphs before? All of you have seen graphs before. Okay, so we will just do a couple of basic things in a couple of lectures and get over these things and then move on. Okay, so I'm not going to define why graphs are important and graphs are useful. Okay, but and there are some notation that I will be using. GVE. I will also be denoting graph like the vertices of graph by V of G. I will also be denoting uh, edge of graph by E of G. Okay, and in this course, everything is going to be finite. Right? So V, Vg, all these are finite numbers. Okay, they are not going to be infinite graphs in this course. No infinite graphs in this course at least. Okay. Okay. So, so the book uses notation like this to denote vertices, number of vertices of this to denote number of edges of G. Okay, but like I might also be denoting like this, which means exactly the same. Okay, just to get you there with what we are doing. Okay, so in graph theory, this is purely graph theory course. So there is this graph theory course. I'm not going to teach from algorithmic perspective. Okay, which means that the focus is very different. Okay, when I teach, say for example, one teaches matching theory, right? So the algorithm correctness depends on the structure and everything, but that's not the focus. It's like focus is can I compute something efficiently? Okay, so but in this course we will largely like 99.99% just focus on graph structures and everything, and maybe next semester maybe we try to learn some algorithmic graph theory and make most of these things computable, but not in this course. Okay, so there are some concepts which let's see what the book says. Okay, so okay, so these are some common notation which is used. This means degree of the vertex. Okay, this means maximum degree of the graph. Okay, of the graph, of a graph. Okay, okay, and what is a delta G? Now am I audible? Okay, I think the battery was down. Okay, so now Okay. Now, what is a, this is not how, degree of V. Okay. And d of G is also called average degree of the graph, and it is denoted by, what is an average degree of the graph? What do you think average degree of graph should be? You sum for every V in V, its degree of V, and divide by V, right? So that's your average degree of the graph. Okay. So what do you think the relation should be between dg, average degree of a graph, minimum degree of a graph, and a maximum degree of a graph? Hmm? So this is the inequality which holds. Okay. Now, all of you know handshaking lemma, right? So now we are done with the graph theory course, which is done in undergraduate courses. Okay, so what's handshaking lemma? It basically tells you that cardinality of E is divided by 2, right? And why it is this? Because for every edge, it contributes to the degree of 2 vertices, right? So every edge is counted twice here, so you divide by 2 to get this number. Okay. Okay. There is also a notion called, which will be important for us, which is called E of G, which is average degree or average number of edges incident to a vertex. Okay. So what is this? It is average number of edges incident to a vertex. So what do you think it should be? It is just simply this, right? So average number of edges incident to a vertex. So I look at the total number of edges, I divide by the number of vertices. That's just definition. You look confused with me. Okay. Yeah. What's the difference between them? No. That's exactly the number of edges. It's sum of degree divided by V. So what is the relation between? So that's a relation between. That's it. Fine. Okay. So let me do my last exercise. Number of, and you understand what I mean by odd degree vertex. A vertex is odd degree if the degree is odd. Okay. So number of odd degree vertices is even or odd. Okay. So in a graph, and sorry, I will not give you a proof. Okay. Is that fine, Kushal? Right? Since you said that like you want from the scratch, so this is from the scratch. So if you want me to prove something, then you will tell me for some of these things. Okay. Otherwise, I will just say that yeah, these are some of the things which is there, and we move on. Okay. So okay, so let's try to prove our first interesting theorem. Okay. Okay, so let's try to understand some of the how people start thinking in graph theory. Okay, so people come up with some definitions and then they try to relate it to the notions which are either known. Okay, either they try to relate it to either the known notions or try to come up with a questions which relates to different concepts. Okay, so so one first natural question is, this is like a, in between. Maybe. Let's look at the phrase. Suppose I told you that that if I told you that delta G is large, okay, whatever that large means, okay, what can you say about epsilon G? That implies that number of edges incident per vertex is also large, okay, right? So if delta G is large, would imply that epsilon G is large. So there is an inherent relation between delta G and epsilon G. So what will graph theorists will ask? The first kind of question, what about converse? If epsilon G is large, does it imply that the minimum degree is large? May not be. Can you give me an example? So this is, you understand, like there are some, so if you notice that in most cases in graph theory, there is one easy part and there is one non-trivial part. So easy part is what generally people will say it's a necessary condition, and the hard part is sufficient condition, right? But it's also about like, okay, if I want converse, then yes, generally it won't be true. So what would be a counter example to this? Okay. Okay. So let's assume for now that graph is okay. I have not used the word. I have not yet defined what connected means. I'll come to that. But like, C is right, right? Look at this, right? Average number of edges per vertex is still function of n, like roughly n. But there is a vertex of small degree, right? But then people will ask, okay, fine, you are right. This is a correct counterexample. But can I say that at least it contains a large subgraph which has this property, or large induced subgraph that has this property? You understand the point, right? Maybe the whole graph does not have this property, but if I say that the average or epsilon G is large of a graph, does it imply that there exists a large induced subgraph which has large minimum degree? Okay, what do you think? At least this counterexample doesn't hold. Or that's one question, or that's like large. Maybe I will fail there. But then I'll probably ask the question, is it, forget about this, does there exist even any induced subgraph with large minimum degree? So let's ask this question. Okay, so okay, given this counterexample, our first basic question to us, does there exist an induced subgraph or subgraph, whatever you want to call it, with delta G, say some function of epsilon G, right? So this is what I mean, like maybe it is not exactly equal to epsilon G, but maybe epsilon G by 2 or something, like, so you ask these kind of questions, right? So my purpose to teach is also to be able to phrase when you read something kind of questions that you could ask, right? So I could ask this epsilon G, right? But maybe that is hard to prove for me. Then I will say, hey, maybe epsilon G by 2, okay? Then I will give up even this and say maybe root epsilon G by 2. Maybe I'll give up this and say, hey, I don't care. Any function of epsilon G is good enough. Okay? So what kind of statement can you come up with? Can you think of a statement? Okay, so here is my proposition, lemma, theorem. Okay. So every graph G with some filler has a subgraph H, okay, with delta H, minimum degree of H, greater than the average degree, but right. So I'm able to give you a subgraph H where minimum degree is at least as good as epsilon g. What should I fill here? Hmm? So you want to say should be equality? Hmm? No, no, no. Delta H. By definition, this is delta H. We'll see. Do we need equality? That's a good question. Let me show to you. This is a quantity. Okay. Why this can be strictly greater? Let me show to you. Okay. Take a click. Take a click. What is the minimum degree? N minus 1. But what is this? It is what is the number of edges? This is the number of edges, right? And what will you need to divide by? It's in the half, right? Again, because it's not an average degree. It's edges per vertex. So it's half of this. This is why this number can be more than this. So is this fine now? Okay. Okay. So what happens? So this is another thing. It's like in general, in graph theory, you will have some very simple counter example to a statement and you must remove them. They are like pathological examples. For example, if I have a single vertex, what is this? Huh? Both are 0. So it doesn't make that much sense, right? I can't show this, right? Because I'm saying delta H is strictly greater than this. So this I can't show, right? Right? Because I mean this is 0 and you're telling me that you come up with a subgraph whose value is strictly greater than 0. Not possible for a single vertex. So what you should? Yeah, so you say with a G with or at least one edge. Okay. Okay, so what should be the proof strategy? Think. Huh? Induction in what? That's a proof strategy. What's a proof idea? What do you want to do? I mean, induction, contradiction, contrapositive is a method to make your intuition a formal. Okay, but what's an intuition? Why should the statement be even correct? That's for one edge. Okay, that's imagine all of you 5 people are there. In total, all of you have 35 buckets. Some 1, 2, 3, 4, 5 people have 35 buckets. Okay, then I want to claim there are some set of people who have at least 7 buckets, right? So if you take all those people, I should be okay, right? What is the meaning of this? Which set of people I'm not bothering to take into account? Exactly. So what should I do? Exactly. Right. So that's a strategy. If there is a vertex whose degree is strictly less than my whatever I want, right? Then they seem not you. They anyway cannot be in my edge, right? Imagine yourself. If there is a vertex V, such that degree of V is less than epsilon G. Is this useful for me? Right? So now let's try to understand. Suppose for this V, I take G minus V. let's consider G minus V. Does it satisfy the property? So suppose this is my intermediary step sum H1. This is my H1 is G minus V. I want to say that, look, I want to construct my H with some property, right? So I want to say, look, even epsilon of H1 is greater than or equal to epsilon of G. Because for this vertex, how many edges are you deleting? You are deleting strictly less than epsilon G edges, and you are also deleting one vertex, right? So vertex per edge is still greater than this quantity. Imagine yourself, okay? So what happens in this case, right? So you are going to delete, so E minus dV divided by, let's say, 3 minus 1. This is what it is. But what are we interested in now? So this is what we are interested in, right? Now, okay, so how to say this? Okay, let's say. And what do I want to show? This is what I want to show. As a ratio, they are more. Okay, is that fine? As a ratio, they are more than this. To multiply now, something should happen. I mean, if you do not understand the intuition and why, like with my bucket, then you have to do the maths. Okay. Not that I did either. Let's do that. Is this fine? So something should get cancelled, right? Right? Now, what I want, dV time cardinality of E, right? Which is dV should be less than or equal to, which is what it is. No? It's like, think, everybody is contributing something, and I have only removed someone whose contribution is strictly less. So everybody else contribution can only go up because you're dividing with less number. That's it, right? So this is all it is. Since you wanted to do maths, I did math. But like, the best way is to always think intuitively why this is true. Maths will go through. Okay, so this is what I'm doing. So every stage, what I'm going to, so I'm going to get a sequence of graph. Okay, so what I'm going to do, I should construct sequence of graph. Okay, so G0 is G. Okay, then I get G1 by deleting a vertex of strictly less than epsilon G. And suppose I stop at GL, okay, some graph GL, this is what my H will be. Okay, by definition, what I'm doing, I'm saying you delete any vertex, in fact, dV less than or equal to epsilon G, and maths is strictly perfectly fine, right? Because until dV is less than or equal to epsilon V, this inequality holds. So I'm allowed to delete every vertex whose degree is less than or equal to epsilon G, right? So why did I stop here? Because I cannot delete a vertex of this. Now, what is the property of GL, right? So property of GL is that epsilon of GL, we have always maintained that epsilon property. So if you notice, basically what happens is epsilon of G1, so basically epsilon of GL is greater than or equal to epsilon of GL minus 1 . Right? So this inequality holds, right? And why did you stop at GL? You stopped at GL because there is no more any vertex of degree less than or equal to this, right? So what is the property of L then? For every V in GL, degree of V is greater than or equal to epsilon. In fact, Next time you shouldn't be doing with, next time when you do, if there's a vertex v such that dv is less than equal to this, is not, you should be picking at that point of time what is a degree with respect to current epsilon, right? I'm still perfectly fine, right? So that will imply the degree of v is greater than equal to epsilon of g. Yes. E of g1, E of g1, g2. Yeah, and that's good enough for our purposes, right? So in each iteration, I will say what is my current epsilon g, right? I pick up a vertex whose degree is less than that, delete it. Okay, so this is what I'm going to. Okay, so this will imply to you that every property that we were delta of h is greater than equal to epsilon of h. Okay, now why h is non-trivial? Why h is non-trivial? Like why h is not empty? We keep doing this, and by end, nothing is left in GL. This is exactly why I assume that G, epsilon of G contains at least one edge. So epsilon of G is not equal to 0. If epsilon of G is not equal to 0, then that implies epsilon of H is not equal to 0, as epsilon of H is strictly greater than equal to epsilon of G, which is not equal to 0, which is rather, let's say, greater than 0. Right? So this implies that you do have a non-trivial subgraph in your graph. Now there are several questions, right, which I'm not going to answer, but like, think for yourself, what is the largest number of vertices H can contain? It's a natural question, like what is the largest set? Look, the graph which we have constructed is basically an induced subgraph, because how we have obtained this, we started with a graph and we defined a vertex deletion operation on that graph. So this is an induced subgraph of my original graph, right? This proof only shows that there exists a non-trivial subgraph with this property. Now my question is, what is the largest subgraph which has this property? That's a fair enough question. I don't know the answer. Okay. I mean, if we sit down, we might be able to do it, but like a priori, I don't know. So this is what I mean by, right? If I started with a n-sized graph with epsilon g this, what size should be achieved? Like what is like L? Okay. What is the largest size H subset of G that exists with the property satisfied by proposition 1? Okay? Okay. Think about it. If my averaging argument seems right, it should be some function of n. I mean, until unless there are far too many outliers, which it could be, maybe, but it's a question worth to think. I don't know the answer. Okay, so that I wanted to tell you about how. So this is the first kind of question, right? If graph has a minimum degree something, then definitely imply epsilon g is large. But in fact, if epsilon g is large, we cannot guarantee that the graph itself will have a large minimum degree, but we are guaranteed that there exists a subgraph, induced subgraph H, which has a whose minimum degree is at least this. And these kind of constructions comes very often when you do something as like, I need minimum degree also large in this. So you immediately say, look, rather than working on the whole graph, let's work on this graph. So some property that will imply the graph itself had some property. Okay. Subgraph is not an induced subgraph. Every subgraph is an induced subgraph, but every induced subgraph is not a subgraph. So this is true for subgraph. I have not defined what subgraph and induced subgraphs are, but I hope you people know what subgraphs and induced subgraphs are. Subgraphs, so just to be uh, on the same page, so given a graph GVE, subgraph is basically some G prime, which is some V prime, where V prime is subset of V and E prime is subset. So these are everything of this nature are called subgraph. Okay, but when I talk about induced subgraph, okay, then so suppose you define G prime, V prime. Now E prime is of specific kind. It cannot. So what is E prime in the induced subgraph? All U comma V in E such that U is in V prime and V is in V prime. So if in V prime there is an edge present in E prime, if there is a pair of vertex in V prime such that there is an edge present in E, then those edge has to be part of E prime. Those are basically induced subgraph, right? So this is why if you notice, like once I know what V prime is, I don't care about E prime because it is completely determined by the set V prime. So this is why people use the symbol graph induced on V prime, because the ones I told you V prime, edges are completely determined. Any pair of vertex here such that it has edge in A, it must be present here, right? So that's a basic difference between subgraph and induced subgraph. So every induced subgraph is a subgraph, but every subgraph may not be an induced subgraph. Yeah. So given, look at this graph, I want to say every graph G with at least or some property H has a subgraph H with delta H this and cardinality of H at least some function of vertex set of G. Yeah, but this is true. It means there it holds with the same size. But at least something it should hold for every graph. I want to say that every graph G which has every G with something has a subgraph H or induced subgraph H with this property and yes, lower bound, lower bound. And it should be true about every graph. Like it's very natural to believe that in some cases I not only I want an induced, like I want subgraph with some property, but I also want some property like subgraph with some large size, right? So I want this guarantee to hold that number of vertices in H is guaranteed to be something. Yes, not constant. I'm also I'm happy even if someone proves log n for me, for example. Okay, any function. I'm also happy if someone tells me that okay, at least I can prove log n, because that is like guaranteed that that is my notion of large. Something which only depends on the function of my input graph G. Okay, and a lower bound, not an upper bound. Upper bound we know H is induced subgraph of G, so H is upper bounded by n. But I want lower bound. Now does this question make sense? Yeah. Hmm. Think what's the problem? Some vertex still could have small degree now because they're all neighbors, but to the vertices which you deleted, right? So you cannot guarantee that I deleted all the vertices at once. Definitely every vertex that you want to delete will be deleted in this process, right? Because, but that doesn't mean that every other, like you will not introduce a new vertex of small degree. You might introduce a new vertex of small degree, right? So that is not good enough. Yeah, it has very high degree, but now everybody you deleted all it, now suddenly he has lost a lot of degree. Is that fine? Okay, so let's, okay, so this is the, I told you a little bit about degrees and relation between them. Now I will talk to you a little bit about, so I'm going to rub this, okay, about paths. Okay, so I hope all of you know what paths are, right? So it's basically sequence of vertices v0, vk, right? Vertices are all distinct. Okay, that's the first thing. And look at any vi plus 1, there's an edge in my graph, right? So this is what these are called paths. Okay, if v0 equal to vk, this is called cycle. Okay, there are some important notions that we will be using, so let me introduce them a priori. Is that, so I'm going to suppose I have two sets of vertices a comma b, okay, and then I'm going to call, oh, p is an AB path. Okay, you know what I will mean by this? So there's a set of vertices here, A and B, and a path which will start from here, but except the first vertex will belong to A, the second vertex will belong to B. Every other vertex here should be outside A and B. It's basically means it's a path that starts at A, like starts at a vertex in A, ends at a vertex in B, but in between it does not use any other vertices from either A or B. Okay, so these are the objects which will be called AB path. Okay, A and B are subset of. Okay, okay, yeah, yeah, they could be equal to. Yeah, you're right. There is no, we are not. Look, as we go along, these definitions will become part of it. Like you don't have to, but it's just that, I mean, okay. So now I'm going to call, say, P1 and P2 are two independent AB paths. What is the meaning of this? It will basically means that you have two paths, okay? Okay, you have two paths, say P1, P2, that their endpoints are there. So they, it could, endpoints could just very well be A and B. I don't care. But internal vertices are vertexes. Okay. People also say independent AB path. So people also will write AB path. Means their endpoints are same, okay, but in between they are disjoint. Okay. So for example, here is A, here is B. This is one path. Okay. Okay. So these are called independent path. Okay. There is also notion of, like, you are given a graph G, and suppose you have an induced subgraph or subgraph H, and you call something H path. So H path will basically mean an AB path where A equal to vertex set of H and B equal to vertex set, right? Okay. And what is the length of the path? I'm sure you have seen an algorithm course. So what is the length of a path? Traditionally, what is used? Number of edges. Okay. It doesn't matter. I mean, you could use anything but be consistent. So let's use number of edges. Okay. Yeah, really, this Zoom has become far more smooth than I thought. Okay, so there are two definitions more. Then we prove. There's something called girth of a graph. What is a girth of a graph? It is length of a smallest cycle. Okay, it's called girth of a graph. There is also called something called circumference of G, which is length of a algorithm question. Can I compute girth of J? And when I say can you compute, of course, I mean I can try all cycles and check and do this. I mean that's not easy to write an algorithm, but and what about circumference of G? Why it is hard? Okay, so this is like Hamiltonian cycle. So this should be hard. But what about this? Let's see if you know an algorithm. Hmm? We can check what? Okay, just to make your life difficult, let me tell you there is no known linear time algorithm to compute girth of a graph. Okay. Then do what? Okay, I compute APSP, all pairs shortest path, and then do what? Hmm? Shortest path. This should give you. So here are amazing set of research problem. You can, if you do very well here, okay. Look at any cycle, right? Shortest or not. Let's look at a shortest cycle. Pick up some edge on this graph. Say A and B. What is this should be? What is it? It's a shortest path. So you compute a shortest path between, like you, for every edge, you compute a shortest path between its endpoint. The smallest of them will give you a girth. Okay. But if you see, this is not a linear time algorithm. Okay. So there is a lot of efforts. In fact, this is even cubic kind of algorithm. Lot of effort to get even compute girth of G, approximate the girth of G in directed graph, undirected graph. Okay, like in sub-quadratic time, and this. Just look at Stock, Fox, Soda in recent time and see how many papers are written. So this is still a problem which is in vogue. But here's an exercise. Okay. Okay. So like here, it is going to take you roughly cubic time. This algorithm. Give me a quadratic time algorithm, but approximation you are allowed is additive. +1. Okay. You are allowed. I'm saying like okay, either you can return me girth of G or girth of G +1. This should be a quadratic time algorithm. Okay. This is something which I have like the algorithm requires new ideas, but it's like okay, do this and do that. That's all that requires, and do this and do that. You have seen in your algorithm course. Okay. So anyway, So couple of more terms. Look at a cycle. This is a cycle. Okay. Now, if you look at any non-adjacent vertices, suppose this is a non-adjacent vertices, and there is an edge between them. These are called chord. Okay. And what is an induced cycle? It's a cycle that for any two non-adjacent vertices, there is no edge. Okay. So, no chord. A cycle where there are no chord are called induced cycle. Okay. So, what do you think is the girth of graph? Is it an induced cycle or not? It is an induced cycle, right? Because if you have a cycle, right, and there is some chord between two non-adjacent vertices, then I can shortcut this and get a smaller cycle, right? So girth of G is always an induced cycle. Okay, so here is a simple theorem, proposition rather. Every graph G, okay, graph G contains a path of length delta G, right? And a cycle of length delta G plus 1. Okay. What is delta G? Do you remember? Minimum degree. Can you prove this? Huh? What? Okay. Okay. Otherwise, we can extend the path, right? Okay. So what it basically says, look at this. Why I couldn't extend this side, or why I could not extend this side? Because all the neighbors of V are present on this path. All the neighbors of W are present on this path, which implies that you have delta G. And why delta? If the minimum degree is 2, why there is a cycle of length delta G plus 1? Right? So what he says again, so look at V, okay, look at start from V, right? Suppose this is where we need that its minimum degree is at least 2 because one of the neighbor is already present here, right? So it has at least one more neighbor here, right? So you go to that neighbor and that forms a cycle, right? And what is the length of this cycle? Why delta G plus 1? Because this vertex is also there and all its neighbors are also present there. So the number of edges or number of vertices in a cycle is same. So this is delta G plus 1. Okay, let me ask you funny questions. Okay. Okay. Again. So do you think you can find this path in polytime? Why, dear friends? It's like just start at any vertex and just greedily extend it, right? No? Okay. Okay. So then that, but then I can ask a very cute question. What's my cute question? Does G contain a path of length at least delta G plus K? Natural, no? I mean, I want to know that do you contain a path of delta G plus 1, delta G plus 2 or delta G plus 5, right? So if I'm trying to describe on what conditions will allow me to have such paths, okay, such paths, that's a graph theory, right? So I'm trying to understand what should be the structure of the graph that, you know, I can guarantee that I can extend my path by at least 5 vertices and 6 vertices. That's graph theory. Okay, but for example, imagine yourself, right? If I had a vertex of degree delta g plus 1, right, then I would have taken that vertex and drawn this maximal path, and I would have got one extra, right? So the only reason I'm not getting this, because if I'm talking about just plus 1, right, it's because every vertex is like delta g, and capital delta G is seems to be same, right? So you understand? Then you start to get some structures. Huh? Look, imagine that if I had a vertex, so minimum degree is delta G. If I had another vertex whose degree was say delta G plus 1, I start from that vertex and I draw my maximum path starting at that vertex. What's the length of this path? At least delta G plus 1. This maximal path will be at least delta G plus 1. Okay. Okay. So the only reason I'm not able to get a path length at least delta G plus 1 is because every vertex has the same degree, right? Which is delta G. So minimum degree, maximum degree are exactly the same. Okay. So you understand my point? So for example, here's a lemma, right? If a graph where minimum degree is different from maximum degree, then there is a path of length at least delta G plus 1. Okay. That's a statement. That's your graph theory. You can make anything as you wish. Okay. But then I will ask, can you come with a necessary condition, like one of the necessary condition for, or I don't know, sufficient, necessary, right? This is not necessary. This is sufficient condition. If you have this condition, then whatever, I'm confused between necessary and sufficient always. But if this condition is satisfied, then I do have a path of whatever delta G plus 2, delta G plus 3. So that's your structural question. So I want to understand graphs structurally. What structures should I invent? Should I put inside that some properties are satisfied? But what about algorithmic question? Do you think it's polytime if I put some k? Do you think, do you know how to solve this problem at least? Say delta G plus 5. Natural, no? Imagine if every vertex has minimum degree n by 3, then you're looking for trying to find a path of length n by 3 plus 5. Okay. No, it's not. It can be solved if I put 5, it can be solved in polytime. But like, it requires different set of tools. Okay. For that, you have to come tomorrow. I will teach you at some point. Okay. But just like, I mean, so recently, I mean, you just pick up any graph theory statement which proves this, and you can ask an algorithmic question and study them, right? It requires extremely, if I put k here, okay, even getting, if I put 5, getting any polynomial time algorithm seems extremely hard question. Just try it out. Like I allow you to even think this, to take whatever you polytime you want, right? It's that difficult. Huh, delta G plus 5. Plus 3. Plus 1 is slightly easier, but 2 onwards, you need whole machinery. No. It's very efficient algorithm. It's n square. But like I'm saying, but there is an algorithm. It's not something which is like, which you would have seen in your polytime algorithm course, though it is a polytime algorithm, right? So I'm saying whatever tools you have seen in your life, and I allow you any polynomial time. Can you come with an algorithm? Any polynomial time for delta G plus 5. Okay. There are algorithms of nature. So I put k equal to 5. but like it's not obvious. It requires a lot of hard work. Okay, this is why like you have to come somewhere else to learn those algorithms. That's not. But my whole purpose is to tell you that even with these basic things which I learned in the first chapter of graph theory course, one can ask lots of meaningful questions. The first chapter is like pick up. Okay. Okay. So this we have done. Any question? And by the way, why do you think it's NP hard when I put K? Why this is NP hard if I put K? Again, right? I can put K equal to N minus delta G and ask Hamilton का. Okay? So it's immediately NP hard. Okay. So another notion people use is this. What is the meaning of this? Shortest distance between X and Y. Okay. So it's basically the length of the shortest path is denoted by dg. Okay. What else is defined? Look. And if there are no xy path, then we denote it by mass infinity. Is it visible, Pallavi? Is this black color visible? Okay. Okay. So there's a notion of diameter of G. What is the diameter of G? What do you think is diameter of G? Is maximum over what? X comma y in V. Okay. So when it is evident that what graph we are talking about, people omit the subscript G. Okay. So this is so you look at all pairs, look at the shortest path between every pair of vertices, look at the maximum of that. That is what is called diameter of a graph. Okay. The definition is there. Okay. Now that we have defined diameter, let's prove another proposition of this kind. Okay. Every graph G contains every graph G contains a cycle every G graph G containing a cycle satisfies that the girth of this graph is 2 times diameter of G plus 1. Right? So what I'm saying to you that look, the length of the shortest cycle in graph is upper bounded by 2 times diameter of G plus 1. It makes sense, but what's the proof? Like, it sounds okay, but notice the girth of a graph in the shortest path is like it's consisting of 2 shortest paths between a pair of vertices. In some sense, right? Okay, but like, what's the proof? Huh? Suppose not. Suppose not, and let's say girth of the graph Suppose not, this is what I can write. Okay, and let's see the cycle shortest length. Okay, yes, next. It is an induced cycle. Between which vertices? So what is he saying is that, look, if it is a shortest length cycle, then there cannot be any chord. Okay. So now let's pick up a two vertices which are at the furthest distance in this. What is the distance between them? So, or rather he says, this implies, let's see, this implies, basically what he's saying is that this implies there exists a pair of vertex, say x and y, such that distance, let's say d in C of xy is, yes, so why it is a shortest path? But in a cycle C, why? How? But is it a cycle? Let's draw. Okay, you will see what I mean. Okay, so what he says that, look, definitely, suppose this is the long part, like this is not a shortest path between x and y. Okay, there exists a path p between x and y of length, agreed? Okay, now let's draw that path. No, I start from here. Why the proof is not done? Why you need? Because this path starting from x, look, if this is a disjoint path, then it's okay. This and this together has given a path of length 2 times diameter of g plus 1. Okay, so that's one nice case. But like it could also be that, but that's okay. But all I'm trying to say that you have to argue. Look at this path and forget this. Forget this green part. Forget this green part. Okay, forget this green part, and you look at the path P superimposed with the path xy path which is on the C. Now this path P, if it is disjoint, you are happy, but look at the first time it intersects, right? First time it intersects, it is definitely going to pick up small portion of black part, small portion of blue part, and both are small, so you have a small side. But you have to say that, right? That's all. Or another way of saying that, you get, I have not used the word, and this is the right time to use the word, something called walk. So what is a walk? Okay, walk is where, of course, consecutive pair of vertices has an edge, but vertices may repeat. Okay, vertices may repeat. Okay, this is why it is called an walk and not a path. And then there's a notion of what is called closed walk. And what is a closed walk? If V1 is equal to Vk. Okay. So now, if you look at C union P, what is this? It's a closed walk of length how much? Look at the path P. Look, I know there exists a path P from x to y of length at most diameter of G. Now you delete this path, this long path between x and y. There is still a path between x and y which is black, right? Right? On this, on the C, which is of length at most diameter of G plus 1. Look, if x to y was of length at least diameter of G plus 1, then the other path has to be of length at most diameter of G plus 1. Okay? Now if you look at this path P, whose length is at most diameter of G. Now now I look at this path P. It intersects somewhere. Right? It intersects somewhere. Now wherever it intersects, like, or rather, that's not the right way of saying it. So rather, look at a path between x and y, okay, whose length is, you know that you have picked up the longest bit. So if you look at a cycle x and y, there's a long side of x and y and there's a short side of x and y. You remove the long side of x and y, okay, and now you're doing some operation. What is that operation you are doing? So imagine that you had a path before of length some z. What you have removed? At least you have removed diameter of G plus 1 by removing this. Now, what are you adding to? Just look at what are we adding to. Now look at this path P. It could just tell me that this is a disjoint from my black path. So, but what did I add? I added something of length at most diameter of G, right? But then then I have been able to find a cycle, another cycle whose length is strictly smaller than the cycle I started with, and that's a contradiction, okay? But P might not be even disjoint. But if P is not disjoint, then what I should say, look at the path P and traverse from X and look at the first time it intersects my black. So now you have some black part which is less than equal to the black part, and you have a blue part which is less than the total blue part. That is still will show you that you have got a cycle which is strictly smaller than the cycle you started with. Okay, and that's a contradiction. So all I'm trying to tell you that you have to consider all these things when you're writing a formal proof. Okay? Okay. Another way of saying is that look at a C and look at a P. Okay? Look at this is a closed walk. C union P forms a closed walk of length how much? Of length strictly less than cardinality of C. It's a closed walk of length strictly less than C. And any closed walk contains a cycle. Every closed walk contains a cycle of length less than equal to its length. That's it. So what we just proved is basically saying that if you have a closed walk, then you have a cycle of that length. Wow, and how will you get that cycle? You start from this. Look at the first time vertex gets repeated. That's your cycle. Or look at look at this. It's a closed walk, right? Right? So look at anything, any other vertex, look at the two consecutive times it repeats, right? You can forget this and you can add this here, right? And if you apply this operation several times, you can get rid of any vertex which in between repeats several times and we're done. So because in between, if look at x and y, right? So look at some two vertex w and the path between them, right? So what is this? I can go from x to w to another w and go. Now rather than doing this, you just forget this path and whatever path was here, you just merge them. This is still a closed walk containing x, but now you have reduced one occurrences of one vertex, which is, and if you do this operation several times, what you can do that in between you will remove every vertex will occur exactly one time, because if any vertex appears twice, you look at the two consecutive occurrences, get rid of them, and you're done. Okay, so every closed walk implies a cycle of that length, because what operation? You're only shortening. You're shortening. Okay, so Okay. The notion of a vertex is central in G. What is the meaning of central in G? Okay. Is the greatest distance to any other vertex is as small as possible. Okay. The greatest distance. So, like, look at a vertex V. Okay. Okay. So now, if I pick up a vertex V and look at the distance to everybody else, right? And pick up the distance, like, and so let's associate a number. Let's say, I don't know how to say. What is the Q of V is among all the shortest distance from V to every other vertex, you choose the one which is maximum. Okay. So what is Q of V? Is maximum over W in V minus V. Okay. D, G, V, W. So this is what Q of V is. Among every, so I start from V, I go to every, look at the shortest path to every other vertex, right? I take the one which maximizes the distance. That is the number I associate. Okay. Now, what is the central vertex? A vertex is central. Okay. Okay. So now suppose I define some notion. Okay. Nu of V is what is nu of G? Okay, is minimum over V. Right. So this is what this means. Okay. So a vertex which achieves nu of G is called a central vertex. A vertex such that which is closer to everybody, right? It's not something that, so what is Q of V? Look at a vertex and look at all other distance, shortest distance. What is the number I associate to myself? The largest of them, right? And which vertex I call central in the graph, for which the everybody else is as close to him as possible, right? So this is what it means, that for a vertex, like, if someone is very far, that is what his measure is. Okay. And which vertex do I want? That everyone who is, anybody who is far is as close as possible. So this is the meaning of the central vertex. Okay. And this has a term, and this is what is called radius of a graph. Okay. So radius of a graph is basically this number. Okay. So I told you diameter of a graph, I told you radius of the graph. What do you think the relation between them are? What can you say about diameter of G and radius of G? Hmm? Diameter of G should be correct. Why? Because after all, radius or something, all we are cared about is shortest path, right? So everything that we are maximizing over or minimizing over is shortest path, right? So we are basically in some sense doing some minimization over some shortest path. And diameter is basically length of, like, is maximum of all shortest paths. But do you think there's a relation here? Can we bound diameter of G as? Do you think so? Is it by memory or do you have a proof? Okay. Okay. Why? Huh. Hmm. Correct. So what C is saying? Look at this. Okay. Okay. That's a, it's a, this is a proof. Okay. So what C is saying is, look at this vertex. Okay. Look at this. This is suppose the radius of this vertex is. Okay. Now, if I understand correctly, okay, look at any two vertex. Okay. Look at any two vertex, say A and B. right? I can reach, there's just shortest path between, there is a path between A and B of length. I go to A to the central vertex with radius of G, and I move from here to here with radius of G. So this is basically not a path. There isn't walk, because maybe this path, if I come there, so there isn't a walk from A to B of distance at most 2 times radius of G, right? So every shortest path, so it means there's a path from A to B of length at most 2 times radius of G. If there's a walk, it means there's a path, because we can do shortcutting. So what we have shown, if we have shown that between any pair of vertex there is a path of 2 times radius of G, it means the shortest path can only be smaller, right? So this is, does it make sense? So this is a proof. This is not a intuition. This is a full proof. I mean, one can make it as a full proof. Okay. Still have 10 minutes. So this is my last lemma proposition of the day. Okay. So So in general, radius, diameter are not related to minimum degrees or average degree or maximum degree, but has a very interesting, cute theorem. Okay. And this is a graph G, of radius at most k, of radius at most k, and maximum degree delta, say d, maximum degree d greater than equal to 3, has fewer than some number of vertices. Let's see what number can we fill it. What it says, a graph G of radius at most k and maximum degree d can contain how many vertices? So how do you think the proof will go? Let Z be a central vertex. Now what should I do? I on purpose draw this ball. Baba, it's not plane. So what do you mean by circle of a center? Correct. Okay. Okay. So let's say let di is okay set of vertices at distance I from J. Okay, I from Z. Okay, so the vertices which are distance I from J. And when I say distance, shortest distance, not that like, okay, please. So can I say something then? Can I say, is this correct? In fact, 0, because we also have Z, right? So, okay, can you tell me how many vertices D1 contains? Maximum degree, right? D. So, no, D0 contains D. Is 1. Because Z2 itself is a distance 0. There is no edge. So, how much is Di? Okay, let's say, how much should you think D2 is? Hmm? D minus 1. Okay. Because what happens is that look at D2, right? They all have at least one neighbor in the previous, right? So one neighbor is gone. So, right? So, yeah. So like what are D2? So their one neighbor is in this much, right? Or rather like this. Look at a vertex in D1. Okay, they have one neighbor to previous one, and they have D minus 1 neighbor at most that it can put in the next one, or less. It can even put less, but not more than D minus 1, right? Because it has at least one neighbor in the previous class. So, and how many of them are there? D into D minus 1. So, how many Di will contain? So, how much is Di plus 1? D into, yeah. So, for I less than equal to k, by induction hypothesis, we can assume that this is what it is. So, now what is size of G? Is 1 plus D times I going from 0 to k. For 0. Look at D1. How many vertex does it contains? So I'm just writing this, right? Because Di plus 1 contains something in terms of I. So Dk contains something in terms of k minus 1. So this is what it is. Now what is this? So D can definitely come out. And what is this? Isn't this some sort of geometric progression? So what is this? What is that number? Hmm? So this will be 1 plus d minus 1 to the power 1, right? No, 1 divided by d minus 2, right? R minus 1, right? So R is d minus 1 minus 1, okay? This is it. So what is this number is, right? I claim that this is definitely less than d times d minus uh, d by d minus 2 d minus 1 to the power k. It should be like that. I'm saying that 1 can be subsumed here. Let's see. What am I writing here? So let's see. 1 plus d times d minus, what is this? D minus 1 to the power, this is what it is, right? I claim that this is strictly less than equal to d times, this is what I'm saying. Is that not true? Okay. 1 plus this is exactly what we want, right? This is 1, but like d minus 2, this is why I assume that d is greater than equal to 3. Otherwise, this math won't hold, right? Okay. So this implies that this is exactly why this implies that this number is now less than, actually strictly less than the way we have. That's it. Okay. Okay, guys.